Well, welcome back, everyone. Looks like we're just about there. Well, it's official. Looks like we're on week 12. On week 12, this one's going to be a pretty pivotal week. We're going to be working through power series, representation of functions as power series. And if we get enough ahead, we might be looking at a Taylor series. I think that's probably much going to be left for maybe next week when we begin working on those. With what we've got going on so far, we have our third exam coming up. This one's going to be a week away from today, which means a little bit behind on putting in the course review information. But what we know for sure is exam 3 only goes up to section 11.6. That's the last section that we completed here. And that gives me a chance to grade the homework, give you your feedback, get your feedback return. So that means 9.5 is going to just be a differential equation, linear function, or excuse me, a linear differential equation. 11.1, we're just looking into sequences. So questions about taking their limits, if they converge or diverge. But from here all the way to the end, this is convergence or divergence of series, all the different kinds that we've looked at. So that's going to form up our third exam. I'll have notes here for review problems and such like we had on the other exams before we come back on Wednesday. Those should be posted pretty soon, Tuesday morning is what I'm thinking. I also am a little bit behind on actually writing the exams. I'm going to have those exams written on Tuesday since they need to be written soon. And I'll start sending out those exams to the various testing centers, Pocatello, etc. And I'll email everyone once those have been sent out to let you know that you can schedule it. And if it's already scheduled, that way you'll know it's all set and ready to go. So with what we've got going on, Monday's class and Wednesday's class will be ordinary classes working with Power Series. When we come back on Thursday's class, we'll definitely have those extra review problems posted. And I'll take whichever review question folks have, no matter what it is on any content here for exam 3. So if you have a lot of questions to start out class with on Thursday, it can turn into just an informal review day. It'll be student-led, so come with questions. I'll be happy to help out. We're actually pretty right on track with schedule, so even giving up the 7th as a review day wouldn't put us too far behind on our schedule at all. But that's my whole set of announcements. Any questions or comments whatsoever, folks, before we get started? Okay, let's get started by reminding ourselves what we did in 11.8. 11.8 is a big departure for what we were doing in these sections, like 11.6. But it starts to answer a lot of questions like, what are we doing with sequences and series in the first place? Well, we're trying to define a whole new function. The function takes on this format. It's a power series only because this time, starting in section 11.8, inside the series is a variable x. X can take on any real number whatsoever, and it's being raised to a power. So your first term being constant is x power 0, then x power 1, power 2, and so on. But because this is a brand new mathematical function, our major question is, when does it converge and when does it diverge? In other words, we're looking for its domain. So scrolling through here, our first power series we took a look at was this one right here. We said it's a power series centered about 3. Reason it's about 3 is because of the -3 right there. If that was a +3 to power of n, we'd say it's centered about -3 using that bit of mathematics to make it come out right. There always has to be a negative and then a number. So that means it would be centered about x equals -3. And it's an important concept because once we expand out our power series and look at all the terms, we can always pick one number where it's definitely going to converge no matter what. We observed, just plug in 3. At x equals 3, the whole entire series, here it is, collapses to just 1. The first term survives, everything else is canceled. And so we say it converges at x equals 3. But again, we want to be a little bit more precise about that. And this is the being a little bit more precise. Any power series, so here's a generic one, has 3 different outcomes. It can potentially only converge at one number, like the one we were looking at above. In that case, we say R, radius of convergence is 0. And the interval is not really an interval, it's a set containing one number. Our author likes to say the interval collapses to a number. In case two, this is the opposite of case one. Your power series above could converge for all x. That's saying it doesn't even matter what you put in for x. This converges some way, somehow. If that's the case, radius is infinity. Interval of convergence, that's the domain, is from negative infinity to positive infinity. And here comes case three. This is the one we analyzed. For most power series, it's going to converge for some x's, diverge for others. And to test that, we immediately just go to ratio test. Ratio test is a really strong hitting hammer on these kinds of things. And for dealing with power series, we mentioned we essentially always use the ratio test, or perhaps a root test if it comes up. The ratio test is a little bit tricky for this kind of thing. And let's pause. I forgot to pull this up. Let's get this document going while we're thinking about it. Okay, so back to our problems. I'd say the weirdest part of all this work is not the start of the ratio test. That's how it always starts. We simplify after expanding things out. And here's a weird part of the ratio test. That x right there is any real number. So the absolute values that's surrounding everything passes through n, 3n plus 3, because n's assumed positive. But it settles on x. So you're always going to have absolute value of x or x minus or plus a number somewhere. We put it out into the front of the limit because the limit only involves n. It turned into absolute value of x times a third. But this is the next weird part right here. We would never do this if we were doing the ratio test in the prior section. Reason we had to do it now is x is a variable. For some x's, it converges. For some x's, this could diverge. So what we've done now is we started with the ratio test, and we went to case one in the ratio test. The less than one here matches this less than one, so we're targeting convergence specifically. So that whole thing became absolute value of x less than 3. By the ratio test, we have convergence in that interval from negative 3 to positive 3. But it's not the whole story. If it was, none of the tests above here on the notes would have mattered, really. We just use ratio test on everything and call it done. The reason we need all of these other tests, starting with tested by divergence, going all the way down to limit comparison test, is because the ratio test always fails at the boundary. What we mean by that is, go back to the ratio test. The limit comes out as 1. Our ratio test is totally inconclusive. We don't know anything about the power series. And that will happen here. If you plug this value back inside here for x, that whole thing turns into 1. And that's the inconclusive case. Ratio test can't help us. Same thing with this positive 3. Throw it back inside here. We have 3 over 3 equaling out 1. And the ratio test again says nothing. It's silent on us. So on those boundary values, we use all of the other tests. So it's kind of weird to rehash out a problem that we already went through the first time, but this is such a tricky process. It's good to just think about it again from scratch. And we'll do a few more. We have, I think, 4 on these notes to take a look at. Since the ratio test fails at the boundary values, negative 3, positive 3, we test those again. We plugged negative 3 into the original power series at the top of the notes, came up with this one. Didn't need a formal test. We knew its name. It's the converging alternating harmonic series. Next, we took 3, the upper boundary. This one turned into the diverging harmonic series. And so we said, radius of convergence is 3. We get a 3 from pretty much right here. This gives a radius of 3. Interval of convergence is from negative 3 to positive 3. The reason we have a bracket there is because of the convergence on the right end. Reason there's a parenthesis here is because we said it diverges at 3. So finally, that right there is the domain of our power series as a function f. Any questions at all, folks? Yeah.
Why is the absolute value of x divided by 3 less than 1?
Right here?
Yeah.
It doesn't have to be, but we put in this part right here specifically, because we were looking at this part. We started with ratio test. We're hunting for all x's that give convergence. So the question in the class is, why less than 1 right here? It's because we go to that part of the ratio test. Less than 1 here is what gives absolute convergence. So the moment we put less than 1, we were answering the question of, for what x's do we get absolute convergence? So we forced in the condition right here of convergence, essentially. Does that make sense on that idea there? Awesome. Again, that's what makes this kind of tricky is we're using the ratio test in a different way, and we have to. The big change is there's an unknown variable all of a sudden, and so now it just depends on what x is. Other questions at the moment? Okay, well, it's a tricky enough process. We have more examples just like the one we went through. And here's the very next one for the day. N factorial times x to the power of n. It's an odd looking series. Zoom in on it just a bit. But like we indicated before, ratio test just gets used all the time. If you're in the context of doing power series and you didn't say ratio test at the start, I'd say that's okay because it's understood you're probably going to use it anyways. But just to be specific, let's state it. Ratio test means we're going to be taking the limit as n runs off to infinity of, let's use the same color coding as before. The successive term in the numerator, the nth term in the denominator, and here's how it comes to all together. In the numerator, it'll be limit as n goes to infinity, absolute value of, because of the index being n plus 1, we go and put n plus 1 everywhere n occurs. So that's an n plus 1 factorial, x to a power of n plus 1. That satisfies the numerator. Denominator is exactly this term here of the series, n factorial times x power n. Once we get to this stage, there's always a lot of simplification. It's almost a guarantee with a ratio test. You wouldn't use a ratio test unless this simplified a lot. And here's how it goes. Take the limit as n goes off to infinity. The standard thing you do right here with a factorial function is you just start expanding it. It starts at n plus 1. The next thing is going to be n factorial. And we stopped right here because there's an n factorial already in the denominator. Next, on base x, we factor this down to x times x power n. And denominator copies in unchanged. N factorial, x power n. We always expect cancellations on this step. And here's what they look like. The factorial functions are gone. And x to a power of n are also gone. Doesn't really leave too much left over. We now have limit as n goes to infinity of n plus 1 multiplying the absolute value of x. And we can take our limits right here. If it just helps for the sake of visualization, oftentimes people take this extra step. Absolute value of x doesn't really impact this limit because it's not indexed by n at all, and n is the value in the limit, or the index in the limit. So absolute value of x is regarded as a constant for that limit. We can pull it out in front and take the limit as n goes to infinity of n plus 1. Any questions or comments at all, folks, to that stage? Okay, you gotta love power series because they are predictable at least. The startup of the power series always goes this way, ratio test, perhaps root test. When we go up to the next step, this whole limit, any volunteers to say what it should come out as? This highlighted part right here. Exactly. I mean, it looks kind of funny because we're used to seeing rational functions, right? But if it's just an n squared plus 1, n plus 1, this goes off to infinity because n goes to infinity. So the whole thing turns into infinity. Notice I don't even write in absolute value of x because absolute value of x doesn't have any bearing on this any longer. And plus, absolute value of x is a real number. There's no actual arithmetic with infinities in the first place. But that statement isn't totally correct. It's equal to infinity as long as x, remember that can be any number, is not zero. If x were zero, the whole thing would just be zero itself for convergence. So we use the ratio test. The output is infinity, except for one exception when x is zero in the first place. And in the summary of these tests, let me scroll this up just a bit. Ratio set test says if the limit comes out greater than one, or even if it comes out as infinity, we don't care. Infinity is fine for the ratio test. We have divergence. Well, that means we're basically done. In the case where we have divergence like this, we are in case one. Or it's case I rather. When I refer to case I, we're talking about way up here, case I. The power series converges only when x is some number specifically. We already know the radius of convergence is zero now, and the interval is whatever that number happens to be. So in case I, what makes case I is this right here. Well, let me actually, for the sake of the notes, let's do this a little bit better. Case I is due to that infinity right there. I think that's a better way to express it. In case I, we have radius of convergence is zero. That means there's exactly one number that it'll converge on. You have to say it here under I interval convergence, even though it's not an interval. Anyone happen to know what the number is that goes here?
Zero.
Good call. Every power series always converges for at least one number, and that's the number it's centered on. You could revisualize this by saying, this is summation and factorial, x minus 0 to the power of n. That would be absolutely algebraically correct, but it reminds you, this is a power series. Forgot how to spell series. Let's try that again. Centered at x equals 0. So we take the center of that and plug it in right here. Notice it's the same as the exception. The exception here that allows a limit to be infinity every time is the value that goes right inside here. It's also the value that you would plug in inside here to get definite convergence. So that means this as a function is totally uninteresting. If you plug 0 inside there, you're just going to get that this equals 1 altogether. Nothing spectacular happens. And the reason it becomes essentially useless as a power series is because, again, the domain is one number 0. It happened because of the factorial being right where it is. A factorial like that up in the numerator very, very limits your convergence, unless there's something down the denominator that restricts its growth. But now we can say by the ratio test what exactly goes wrong and not saying factorial is a problem, waving our hand at it. Well, that one's done. Sometimes these are really fast problems. Sometimes they're extremely long. It just depends on the power series. Any questions or comments whatsoever, folks, getting through this one? Okay, so this one's kind of a refresher. By the way, this one right here, when it came out to like this was our case 3. We set it on the other one, so just for the sake of completing the notes, case triple I for case 3. So let's take a look at our next one coming up. You can already tell it looks like an adventure. There's lots going on this one. And it's not even easy to say what it's centered about. The algebra, the format on this is a little bit off in a certain sense, but let's say it here just to be specific. It's a power series centered at x equals, kind of tricky to see. Any volunteers for what the center is of this power series? It's not 4, but if you're thinking 4, you're on the right track. It just involves a little bit more. So it comes from right here when we go to give the center. And for another hint, good call. Whatever the center is, it's the value you place on X to make that whole thing a 0. That's how you identify the center. Usually it's not so bad to identify because typically a power series would be written in this kind of way. We get there. Geez, it's hard to get to that spot. It's often more often written this way. The center would have been 4 in that case. But if there's an extra coefficient on X like that, it affects the center. And like you said, this one is 5/4. In other words, it's the value that makes this term right here go to a 0. Let me take a look. Yeah, absolutely. That wouldn't have been a 0 at all. 4/5 altogether. I feel like I should go through the motions now. If you plug in 4/5, the 5s cancel. It's 4 minus 4 for a value 0. Well, we have a power series centered at 4/5. That's helpful information, but what we're doing next is jumping right away into ratio, not ration, ratio test. So let's work this one out carefully. Limit n goes to infinity. This setup is always worthwhile, especially when you're doing this as a homework problem, because it's all about being methodical, getting all the components in the right place, because there really is a lot of moving parts until the cancellations actually happen. So take the limit as n goes to infinity. Here, this time our power series has a whole fraction. So first thing we're writing in is just the numerator an plus 1. It's going to be 5x minus 4 power n plus 1 divide by n plus 1 to power 3. So that takes care of the first term, the numerator. For the denominator, we're dividing by this, and huge time saver. It just means to multiply by its reciprocal. So we write in n cubed over 5x minus 4 to the nth power again. We've got it, folks. This is the format the ratio test takes. All we're doing next is simplifying this down, taking the limit. And by the way, for a great simplification, here's one way you can cancel. That whole thing is gone. It leaves one factor behind here, so let me convey it this way. This is me saying the nth power has been canceled off from this nth power. All that's left behind is 5x minus 4, and we'll even drop the power 1 on the next step. Does that make sense to folks visualizing cancellation that way? Awesome. Next thing that's going to happen is we're taking the limit as n goes off to infinity of the absolute value of a bunch of stuff. But this part, where the red dot is the only thing where absolute value is actually pertinent. That has the chance of going positive or negative. So centers like this, 5x minus 4 in absolute value. Left behind is n cubed in the numerator, n plus 1 cubed in the denominator, and this is our limit we're going to take. Here's our optional step. It's for visualization only. Take 5x minus 4 in absolute value. It's constant since the limit is relative to an index of n, not x. Left behind is n cubed, n plus 1 cubed. And so this is the limit we have to take. And by the way, it's not a bad limit. Those shortcuts we've been using work out really well on this one as well. Anyone happen to know what is the limit of this thing? It is a limit 1, absolutely. You can imagine if you expanded out the denominator, it'd be an n cubed plus a bunch of other stuff. But the most important thing is there's a tie in the degree, coefficient of 1 with n cubed above and below. And so this whole thing is limit 1. So we've got absolute value, 5x minus 4, multiplied by 1. Actually, kind of like that highlighting. Kind of just shows where the 1 comes from. So let's go with that. We're using the ratio test in a really odd way. It's always good to reiterate this because it's weird enough, you know? We're going here. We don't know if it converges or not. It depends on x. So we make the condition, this comes out less than 1, and solve for those x's that make that condition true. So go to case 1 in the ratio test, write less than 1, and now we're going to be solving this inequality right here. Let's drop it down to a new line, but maybe doesn't hurt to say, just to be specific on what we've done. This is convergence for ratio test. So next step, let's take this whole thing and just drop it down so we can focus on inequality. 5x minus 4 is less than 1. Here's a kind of a decent shorthand. We can already say what the radius of convergence is, because the -4 is just going to shift things around. It's more based off of this 5 right here. It gives us a radius of 1/5. We need to explain that a little bit more, but that's a decent shorthand just on its own. Let's explain it more by just solving this inequality even further. You can drop absolute value and say -1 less than 5x minus 4 less than +1. Now we have to solve this inequality. So add 4 to both sides. We get 3 less than 5x less than 5. Divide by 5 to get 3/5 less than x less than 1. So my claim was, from just right here, you could tell the radius is 1/5. And the reason that's true is, here's what we've got going on so far. We have a lower bound of 3/5. We don't know if it converges or not there. So I'll just put a little open circle with the 3/5. The center was where? 4/5. So here's 3/5. Over here is 4/5. That's the center. We know we have convergence there. And then this is the upper bound, but let's call it 5/5, just to emphasize. The distance from here to here is the radius, which is 1/5. So that's how this all comes together. Essentially, what we're trying to do is find the domain of that function way up here at the top. I think we can undo that color coding though. Well, we know the radius of convergence, it's 1/5. We don't know the interval convergence. All we can say for sure is that it converges from here, where this shading is, up to here. Our goal is now to say, what happens at 3/5? What happens at 5/5? Yeah.
On every ratio test that comes out to have like a greater than less than 1, would that always give you the right radius?
Going from here to here? Oh yeah, absolutely. Yeah, that's always going to be an effective way to find the radius. Yes. Other questions at the moment? Okay. Well, now that we've gotten to this point, we can say we are in case 3 or III. We have to test the boundary values now. So we need one test when x is 3/5, another test when x is 1. So for the next phase, we say, let x equals 3/5. Then our power series, we still call it summation an. We need to say what it is though, so let's remind ourselves. Trying to take a screenshot, there we go. There's that power series. We'll just tuck it away over here as a quick reminder. So we're plugging 3/5 there. We'll get summation as n goes from 1 to infinity. 3/5 here is going to give us 3 minus 4, so it's -1 to the power of n, divided by n cubed. This time, this is not the alternating harmonic series, but it is an alternating series. So we can use the alternating series test on this one. This is a pretty big step up, however, to get to just this stage. Any questions or comments at all, folks? Writing out that power series there. Okay, well, observing the -1 to a power, we can use the alternating series test. Not a bad idea. Imagine not a bad idea to pull this up as you're doing these as homework problems. Imagine this is like your sheet of notes you might be taking to exam 3. You want to become ultra familiar with where everything is at. We're going to the alternating series test. We define this new thing, a sequence containing just the positive terms. We have to argue that it's a decreasing sequence and that the limit is 0. If we can do those two things, we have convergence. Looks like it should be doable for this one. So let's start by saying, highlighting this, let Bn equal 1 over n cubed. Well, the numerator is constant. The denominator grows without bound as n gets larger. So we can say, then Bn, as we go from 1 to infinity, is decreasing. And when we go to take the limit as n goes off to infinity of Bn, we're taking the limit of 1 over n cubed. But that's definitely a limit of 0. When we have degree 0 in the numerator, a cubic in the denominator, this goes to the limit of 0 no matter what the rational function is. So long as the denominator is of higher degree, that's the foregone conclusion. But then what this all says is the series converges. Notice what that allows us to do. Imagine the stuff in orange is your scratch word. You just found out it converges at 3/5. That means the boundary value is included in our interval of convergence now. So we have more information on what I is going to be. We already know R is 1/5. But now it just depends on what happens at 1, that 5/5 we wrote in. So we do it all over again. We let x equals 1. We should pause here, though, catch our breath. Any questions, folks, for up to this stage of the process? Okay, here's our next step then. We say, let x equal 1. That's coming from right here. When x is 1, summation an is just our name for the original power series, this one down here. It turns into and goes from 1 to infinity. Right here by the red dot, plug in a 1, and now we just have a 5 minus 4. That means we're looking at 1 to power n, and that's just a 1 altogether. So it's a 1 over n cubed, and that's a way faster test. Let's just hit it with the p-series test. It goes like this. That's the most important part of the p-series test right there, that 3. We can now say p equals 3 greater than 1 implies it converges by p series test. So p-series test, again, is kind of a fantastic test. You're just saying what you see in the problem, basically. Don't forget to write out what the power is. If you forgot to say greater than 1, no big deal. I put that in the notes just as a reminder. That implies convergence. Kind of a helpful way, if you get into that habit as well, for memorizing these things. But all we needed to do for our total conclusion is indicate the power, so I know you know what the power is, that it converges, and what the test was. That means, well, we got convergence again on this one. We can fill in that dot, and this is now just a number line showing us the domain. To summarize, we'll put a big ... to say this is our conclusion. Radius of convergence, scroll up for a moment. Just from right there, it's implied to be a fit. So let's say it down again. Interval convergence, this is the domain of that function right there, the power series function, is, we said convergence on both ends. So it's from 3/5 up to 1. No harm if you put 5/5, but usually we simplify these things. That's more just for the sake of visualization. I left it that way. Well, we did it, folks. What all of this is saying is that's a true mathematical function right here. You could call it f of x. In fact, we will be calling these things f of x in the very next section. And as a function written as a power series, it only makes sense if you put in anything between 3/5 and 1, including the boundary values, but nothing else. If you try to evaluate f at 2, for example, it's undefined because the power series would have diverged. Well, we have one more to take a look at, I believe. But any questions at all getting through this one? You know, the good news about these problems, doing them right now, right before exam 3, is you'll notice that a lot of these power series are just forcing us to go through everything. Tests for divergence can come up, geometric series, P series. We just use the alternating series test. Comparison tests both could come up when you're dealing with power series. So think of these as gigantic problems where you're reviewing a lot of what's actually on exam 3. Let's try this out one more time for this one here. So we're looking for a quick border. There we go. I think this is our last one. Yeah, it looks like it is. This one's a little bit tricky because there's a factorial in the numerator. There's another factorial in the denominator. It's not really clear what should happen with this kind of thing. We just have to go through the motions. In the denominator, the factorial is larger, so this one might converge for all real numbers or might just converge on a specific domain, like this interval here. Nonetheless, whatever we do with it, this is a ratio test problem. So let's immediately take the limit as n goes off to infinity, an plus 1 divided by an. But looking at this power series a little bit more closely, it's pretty involved. And sometimes when there's lots going on right there, it might be a good idea to just start breaking these down a little bit more. So before we put everything together in the limit, let's just take a really close look at an plus 1 and see what we can do with it. So an plus 1 means go here, here, and here. Throw an n plus 1 in all of those positions. We've got an n plus 1 factorial, x power n plus 1, 2 times n plus 1 factorial. Notice right here by the red dot, that's actually kind of tricky in a way. There's a little bit more that goes on with that factorial. This is not, say, when we go to write n plus 1 here, it's not 2n plus 1 factorial. It's a little bit more trickier. It's really 2n plus 2 factorial since that 2 distributes in. To me, that's one of the easiest things to miss on this problem right here. And it's also one of the reasons why we're looking at this really, really carefully before we throw it back in the limit. So working with this again, let's break it down even further and call this n plus 1 factorial, x power n plus 1. Denominator is 2n plus 2 factorial. So let's simplify it even more. Standard thing we do with the n plus 1 factorial is write in n plus 1, and then stop expanding right there. Leave behind an n factorial. Then we have an x times x power of n. Below, we need to expand this one even further. It starts at 2n plus 2. Next is 2n plus 1. Then that's a good stopping point because the next one is 2n factorial. And that's good because 2n factorial is going to come up again a second time and just cancel off. So that's the surgery we would do on an plus 1 to make this limit as pleasant of an experience as possible. Any questions at all, folks, working with the exponents or factorials? Okay. Putting this all together, the limit now turns into, let me do a little arrow. I think I need to go down a bit. equals limit as n goes off to infinity. Let's first substitute in what we wrote out here on the margin. So n plus 1, n factorial, x times x power n, all over 2n plus 2, 2n plus 1, 2n factorial. I think we've got it all in. Then we multiply by the reciprocal of this, highlighted in green right here. That's an. So take the reciprocal. We have a 2n factorial. Divide by n factorial times x power n. Really, the worst thing about this is that there's just so many little components to this, so many different factors. It's easier to just miss something and not get the whole thing in. Speaking of which, it's also a good idea to just double check we've got it all in. Does that look right to folks so far? Okay, well, finally, this is the fun part, the canceling. It also kind of answers, why didn't we expand this even further? Why did we stop at 2n factorial here with the blue? It's because once we got to 2n factorial, it cancels with the other 2n factorial in green. So that was a good stopping point for us. Next, we stopped here at n factorial because it'll cancel with that factorial. And you know what? There's even more cancellations inside of here. That 2n plus 2, if you factor it out of 2, it's really just an n plus 1. So these both reduce as well. Maybe we'll do that on the next step so it doesn't get too crazy. But I forgot to x power n also cancels. And this is what our limit looks like so far. It's a limit as n goes to infinity. The absolute values don't totally vanish. They settle right here by the red dot. So we go n plus 1, absolute values of x, absolute value of x rather. Down below here, just to simplify further, we can factor out of 2. Leave an n plus 1 behind. Next factor is 2n plus 1. Now here's a bonus cancellation. That part of the problem has canceled off. And let's see. Absolute value of x, if you prefer, can take it outside the limit to focus on the moving parts as n goes off to infinity. And really all that's left now in the numerator is a 1 over twice 2n plus 1. So we're about there, folks. We just need to take this limit here. But that's a great limit in a certain sense. It's 0, absolutely. We have degree 0 in the numerator, constant. The denominator grows without bound as n goes off to infinity. So the whole thing turns into an absolute value of x times 0. And 0 here is the value of this limit. Whenever this happens, and this is the first time on these notes that it's happened, this is case 2, or double I. The reason it's case 2 for double I is because the whole thing is just 0 now, and it's 0 for all x. Saying for all x is huge. It means it doesn't matter what you do, what you plug into the original series here at the very top. The limit by the ratio test will be 0, even if x is like 10.3 times 10 to the power of 500, an obscenely large number, makes no difference. We've got convergence. Take another look at this situation. In the ratio test, less than 1 implies convergence, but we get 0 by default each and every time. So what we get to say is it's absolutely convergence for all x. The way we express that is we say r equals infinity. I, this is the interval of convergence, or just the domain of the function f, is from negative infinity all the way on to positive infinity. So that's our conclusion on the ratio test. Notice case 2 is fantastic, and so is case 1, because in both of those cases, once you complete the ratio test, you just go to make a conclusion and no further testing. It's case 3, we've done it twice on these notes, that there is further testing at the boundary values. Well, any last questions, folks, about power series so far?
One,
Yeah,
X is not something that always was attention on.
exactly, absolutely. And
Is that what
Yes, absolutely. So there's like this huge like overlap of center here, the center here, and here. So those are always going to fall in line in that same exact way. Absolutely. Other questions so far? Let me scroll back down to that last problem. Okay, well, we're not done talking about power series. In section 11.9, we're just taking this a little bit further. We keep hinting when we write down an interval, it's really just the domain of this as a function. And it's sometimes, a few times on the notes, we literally just wrote equals f of x, just to be specific. So now we're going to take that analogy even further with 11.9, representation of functions as power series. In the reading, our author's been hinting a lot with this equation right here. This is pretty fantastic when you're looking at the geometric series. Geometric series is usually not indexed that way. In the geometric series test, we usually start as n equals 1. The power here is then n minus 1. And we have a coefficient a. So this as a geometric series is indexed in a different way. We're starting at 0. If the index drops by 1, up here it should go up by 1. So that's why it's an n, not an n minus 1 like we see here. Also, for this particular power series, we don't have a value of a. So that's why there's no a right up here whatsoever. And let me see if I can add just some temporary annotation. When we go to write this out, we have convergence when this happens. In our notes, that would imply absolute value of x less than 1 gives convergence. This is a really strong statement. It's not like, say, the ratio test. In the ratio test, it fails at the boundary values, but not this one. We have convergence exactly when r is less than 1 or x less than 1, and divergence elsewhere. So we never test on the boundary values. It's guaranteed to diverge on the boundary. Next thing that happens that's also interesting is you form this total sum when convergence occurs. This is one of the very, very rare series where we can say what the exact sum is once it converges. Because a is 1 on this one, we just have a 1 here. Then we go 1 minus whatever the common ratio is. For our common ratio, we're just writing in an x instead of an r. So that's the only difference. This is now essentially just the geometric series. So focusing on this a little bit more, it says we have convergence in this interval from -1 to +1. The radius of convergence is 1. So this right here is an extremely strong statement. It's important enough for us to make an actual big deal out of this. Unlike the ratio test, here we obtain I with no further testing. It's good to remind ourselves, why did the ratio testing further testing? It's only because of this unfortunate part of the ratio test. It can become inconclusive when the ratio, or the limit rather, came out as 1. But the same is not true with the geometric series. If we're right at, say, +1, we know it diverges by the geometric series. Again, that's fantastic. This statement right here could save you probably, I'd say, 45 minutes on this homework assignment, knowing you needed no further testing. Well, other things that we're going to think about when we go to use this geometric series to represent a function as a power series is it's all about this. We work at going left to right. We're starting off with something that looks like the total sum, and we're trying to get to here, power series representation. So we match this format as much as possible. We want a 1 in our numerator. We want a 1 minus in the denominator. If we can make that happen, it's not going to be x right here where the red dot is, but whatever it is, goes right there. We raise it to the nth power, and we've got our representation. We'll try that out with a few functions down below just to see how it goes. And then further on these notes, these are actual functions, so we'll see how to actually differentiate them and integrate them, even when they look like this. So we're going to learn how to differentiate power series or integrate them as well. Well, any questions, folks, with this theorem, essentially the geometric series test with a different look? Okay, let's give it a try. So let's also take this along with us, because this is the most important thing to look at every time you work one of these types of problems. They are slightly weird, so let's go very carefully. We've already got our first want. We need a 1 in the numerator, so we go in, fix the next thing. We want x to be in the second term, so let's just rearrange the terms. -4 plus x. So our second want is x is right where it needs to be on the second term. We need a 1 there, so the next thing we have to do is factor out -4 from the denominator. It would look like this. -1/4 times a fraction, 1 over, where the red dot is, it turns into a positive 1. Divide by -4 here gives us minus x, divide by 4. And even though they're not necessary, I often put parentheses right here because it's now a reminder. This part is the magic thing that goes here once it becomes a power series. But that only works provided, should have captured a little bit more. Let's just write it in. This only works provided the absolute value of x is less than 1. That's why the radius of convergence is 1. That's why the interval of convergence goes from -1 to +1. So let's actually say that right here. Absolute value of x less than 1. Let's do a new screenshot. Okay, I think this is the better way to think about this. There's two things we have to do at once, and the reason I'm making such a big deal out of this thing that we wrote in is we're going to find a power series representation, but at the same time, we also need to express the interval of convergence on these problems. Not as worried about the radius, just going for the interval, in other words. But we find that by this portion right here. So here's the next step. We'll say that this equals summation, n goes from 0 to infinity of this part right here is being raised to the nth power. So we write x over 4 to power n. And if this is all we're doing with that power series, you don't have to take any further steps. But later on in the notes, we will be differentiating and integrating them. And it turns out this next step is extremely important in that case. So I encourage you to take this additional step. Equal summation from 0 to infinity. You absolutely want to break up this exponent, raise x to the power n and 4 to the power of n separately. And you also don't want to do this. Sorry, it looks like I dropped the -1/4. Should have carried in over here. And it should have carried in, let me just scoot those equality signs over here. -1/4. Yellow to show that omission. It's always awful to miss a problem by just forgetting to copy something. But that also means there's one more step on this, writing out the power series portion. We can also say that this equals negative summation as we go from 0 to infinity. That's a 0 down there. X to the nth power, at 4 to the power n plus 1. So in other words, we just took this power 4, brought it into this denominator, which bumps up the power by 1 more. Wouldn't hurt to add a little bit of yellow just to convey that. Okay, let me see if I can move that down. There we go. So our f of x is now this as a power series. But it's not the complete truth right here. This equality right here is suspicious. Because when you look at this function, its domain is all real numbers except 4. But this is a power series, that's not true. The domain is actually highly, highly restricted now. So when we went over here and dropped x over 4 in this location, we don't have x now, but we have x over 4 in absolute value less than 1. So we'll say provided absolute value of x over 4 less than 1. When we're saying provided, we mean this equality is true provided x is small enough to make the absolute value of it divided by 4 less than 1. We can also say then absolute value of x has to be less than 4. That's us multiplying both sides by 4. And then here's our conclusion. Therefore, the interval of convergence, what's referred to over here, I, is from -4 to +4. Then the whole procedure just stops. Again, this is the part where this comment here in orange is in play. If we were doing problems in section 11.8, we always test the boundary values with the ratio test, but here there's no need. We automatically get the interval of convergence. It's guaranteed, in other words, to diverge at -4 and at +4. And you can test that out. Throw a 4 inside here. You're just going to have summation 1/4. In other words, you're adding 1/4 repeatedly for all of time. That would diverge to infinity. But we did our first one, folks. This is now a mathematical function. Sure, its domain is restricted a whole bunch, but there's a lot of things that you can do with functions like these. In other words, just to take a preview in the notes, using these kinds of methods, we can integrate functions like that. These would be extremely terrible to go at with first principles, trying to find an antiderivative. Some of them don't even have elementary antiderivatives, but still, we can integrate this kind of stuff. But we need to make power series work for us to have that happen. So that's the punchline with what we're doing right here. Sure, that's not the most world's exciting function with its limited domain, but we're trying to work with functions much like these, just so we can integrate and differentiate more and more things. Any questions whatsoever, folks, with running through this one? Well, let's try it one more time then. Well, there's actually more on here, but here's our part B. I think we have enough time to try out this one, make it our last one for the day. Then when we come back on Wednesday's class, we'll work towards the rest of these notes, potentially take a look at Taylor series and Maclaurin series if we have enough time. So let's give this a try again. It's really just a game of match this format with the understanding, with the highlighting here, it might not be X anymore, but whatever that is, you just plug it right inside there. So our first one is a 1 here by the red dot, and also right here as well. That means we should just factor out 3/5 as our very first step. We have 3/5 multiplying 1 over 1 plus x squared over 5. It's getting closer. The next big thing we want is that right there, a negative sign in the middle. It can always be done. Just include double negation right here. So you'll get 3/5 times 1 over 1 minus negative x squared over 5. At this stage, we've matched the format to the T. We have a 1 in the numerator, a 1 minus, and then a bunch of stuff that's not so friendly like this, but it has matched the right format at least. We plug all that stuff right inside here, and now we've got a power series going. This is now equal to summation from, oh, let me not forget that one step. Don't forget you have a constant in front. It's easy to get carried away with the most exciting step here, but carry the 3/5 first, then take a summation from 0 to infinity, and go negative x squared over 5 to the nth power. So that's essentially this equation down here with something other than an x written in. We're mostly through with this right here, getting to this step. Does that make sense to folks on how we landed on that power series? Okay. I just want to emphasize one more time, for these problems, if you leave it like that, no harm done, because we're just done with it at that step. But a lot of our power series do have additional steps that we're going to be working on. So here's a good idea just for basic principles. Let's write 3/5 summation as we go from 0 to infinity. Split up the power n 3 different ways. We have -1 to the nth power, x squared to the nth power. That would turn into x of 2 times n, the exponents multiply. And down below, 5 to the nth power. It means we can now combine this base with the denominator as well. Nowhere for the 3 to go though, so usually we leave it outside of the series this way. So our power series is 3 times summation from 0 to infinity, -1 to the n, x to the power 2n, over 5 to the power n plus 1. You'll notice our power series are typically written in this way anyways, and that's for good reason. A power series left in this format is difficult to work with if you're differentiating and integrating, but in this format, not as much trouble. So we've got it, folks, a power series. We still need an interval of convergence. And so the interval of convergence is a condition right here on that equality. Everything we said is correct, provided that, let's say it may be this way, the absolute value of -x squared over 5 strictly less than 1. So that's this portion right here of the geometric series test. It's a weird test because we're using the test backwards, starting from the sum, and then stating the condition to make that sum correct. So let's start working with this. Absolute value kills the negative sign, and we can multiply both sides by 5 to get absolute value of x squared. Well, that's just x squared since it's positive, less than 5. Next thing to do is to take the square root of both sides of this equation. And that takes us to one of the weirder identities for the absolute value. Square root of x squared is just another way to say absolute value of x again. So when we go and use it here, we now have on the left-hand side, absolute value of x less than root 5. From this statement, it leads directly to the interval of convergence. We can say I equals -√5 to +√5. So that's how this always kind of reconvenes. Whatever the number is right here, it implies that interval. So altogether, what we've said is that function whose domain is naturally all real numbers, there's no problem in that domain. It could be written in as a power series. There it is. But the trade-off is you've severely limited your domain to between -√5 and +√5. If your problem uses that domain naturally, then that's excellent. You can do a whole bunch of things with that as a power series. Well, that's our second one down. When we come back for Wednesday's class, we'll practice a few more and then look into the theorem that allows us to differentiate and integrate these kinds of functions. Well, any last questions at all, folks, before we call it a night officially? Okay, well, have a great night, folks. We'll take a look at these notes next time, and then after that on Thursday, we'll be essentially reviewing for our third exam. Have a great one, drive safe, and I'll see you all in Wednesday's class.